We're looking at dot product today of vectors. And so we looked at addition, subtraction, multiplying by a scalar, these operations. So today's operation is about multiplication of vectors. So what a dot product is a multiplication of vectors. And it's really important to remember that the dot product of two vectors produces a scalar. So just like a number, not an x and a y, just a number. Okay, so I think about dot product as being like added energy. So if I look at my vector u here, which is 3 comma 0, and my vector v is 2 comma 4, I can see that vector u is going right across the x-axis in so horizontally by 3 units or 3 energy units. So what I want to do is figure out if I multiply u times v, how much extra energy do I get out of this? So the problem is that v is not going in the same direction as u. So what I need to do is look at v's x component. So I can see that v is going in the direction of u for 2 units. So I can say that my original 3 units are being multiplied by an additional 2 units. So in order to figure out the dot product, what we do is u1, u2, this is v1, v2. The dot product is u dot v is equal to u1, so in the x direction, times its multiplier, times 2, plus in the y direction is 0 times 4. So u dot v is equal to 6 plus 4. Oh, just kidding. 6 plus 0, which is just 6. So the dot product of u plus v is just a number, just 6. So another way to look at dot product is here. If I look at my drawing here, the magnitude of u, so right here, u, so the length of u, times, if I call the angle between these two vectors theta, I would be calculating the, so this first initial vector times the length that overlaps, which is cosine theta times my vector v. So the overlapping part right here, I'm doing it pink. The overlapping part right here is v, the magnitude of v times the cosine of theta. And that gives me another way to give me my dot product. Okay, so remember these two calculations, they're a little bit different. So if you don't have theta, you're going to use the first one. If you have theta, you're going to use the second one, basically. Okay, some properties of dot product. So remember that all the bold stuff are vectors, and all the, like right here, the c is a scalar. So just a plain old number. So if I'm going to multiply two vectors together, vectors, you can multiply them. U dot v is equal to v dot u. Okay, so let's go ahead and look at the first one. If I have u is equal to 3 comma 4, v is this, and w is this. So we're going to find the following. So u dot v, so what do I get out of u dot v? Well, I'm going to get a scalar because dot products give me a scalar. So I'm going to go ahead and be like, u is equal to 3 and v, so we're going to call this u1, u2, v2, v1, v2, w1, w2. Okay, so I'm going to do for this inside part, the dot product is u1 times v1, so the x parts, plus u2 times v2. That'll give me just a number, and then I'm going to multiply by my vector w. Okay, so I get 3 times -2 plus 4 times 6. That's just a value, a scalar. Okay, so -6 plus 24 is 18. And then I'm going to replace vector w with its components, so -1, 1, -1. And from yesterday's video, you'll remember you can multiply by a scalar, giving me the vector 18, -18. And that's the answer to that one. Okay, let's look at the next one. So I have u times 2v, or dot 2v. So let's start with this 2v. So we're going to have u times 2 times the vector -2, 6. Okay, so I get u dot -4, distribute our scalar in, -4, 12. Okay, and then I can replace my vector u with 3, 4 dot -4, 12. So I'm going to have u1, u2. This is, let's call it something else. Let's call it q1, q2. So we get the x components, we multiply, so 3 times -4 plus 4 times 12, giving us -12 plus 48, which is 36. Okay, next. Try this one on your own. You know what? We're going to change this one. Just kidding. We're going to do u plus v time dot v. Okay, so when I add vectors, what do you get out of that? You get another vector. So I'm going to do u is 3, 4 plus v is -2, 6, and we're going to be doing the dot of v. So we get the vector 1. So 3 minus 2 is 1, and then 4 plus 6 is 10. Okay, so that's our new vector, u plus v. Okay, times vector v, which is -2, 6. And then how do we do dot product? Well, we do the x's times the x's and the y's times the y's. Okay, so we get 1 times -2 plus 10 times 6. So we get -2 plus 60, which is 58. So we're getting an added energy, like when I multiply these two vectors together, the original the original vector gets like a times 58 power. It gets added energy, basically. Okay. All right, example 3. The dot product of u with itself is 7. What is the magnitude of u? The magnitude of u is u times u is equal to the magnitude of u squared. That's one of our properties. So I know that since the dot product with itself is 7, that would be this, the dot product with itself is equal to 7, that the magnitude of u squared is equal to 7. So just solving for magnitude, we're going to root both sides. I get the magnitude of u is equal to the square root of 7. If we look at this on the graph, I have a vector with the magnitude of root 7 multiplied by another vector with a magnitude of root 7, my total magnitude is going to be 7. So it's like a times root 7 its power. Okay. So use the dot product to find the magnitude of u is equal to -8, comma 15. So this is just like another way to calculate magnitude, or like to kind of prove that this u dot u is equal to the magnitude of u squared. So if we think about u is -8, comma 15 dot -8, comma 15. I know you could use Pythagorean theorem here. This is, like I said, it's just another way. Okay, is equal to the magnitude of u squared. So how do we do a dot product here? Well, that would be -8 times -8. So the x's plus the y's, 15 times 15, which is equal to the magnitude of u squared. Hey, doesn't this look familiar? Yeah, Pythagorean theorem. Okay, so we get, when I add these together, I get 289 is equal to the magnitude of u squared. And then, so square root, I get the magnitude of u is equal to 17. Woohoo! Okay, let's go for another video.